title of this talk is Determination of Quasi-Linear Terms from Restricted Data. So here in this title, there's several notions that I would like to clarify through this talk, including first this idea of determination of quasi-linear terms, the other one, this notion of restricted data. So I will try to clarify this different notion appearing in this title. But let me start first by giving the statement, the general statement of, just a second, yes, it's better that way. Can you see it still, or?
Yes, we can see it.
Yes, okay, because I couldn't see the upper side. Oh, it's maybe.
I'm-
Oh, no, that's okay. That's okay. No,
Mhm.
sorry, just a second. I always have this kind of problem. Uh, okay, that's better. So we'll start with the general statement of this problem, which will be considered with omega, which will be an open-bounded and smooth set of Rn, n being higher than 2. And in this open set omega, we will consider this type of elliptic type of equation. So it will be an elliptic type of equation whose solution will be U. The equation will be considered on this open set omega, and it will involve some parameters which will depend on the solution and on the gradient of the solution. So this is the type of equation that we consider. And we associate with this equation the following boundary value problem by considering Dirichlet boundary condition, which is imposed at the boundary of our open set. So here, the particularity of this problem comes from the fact, the first one comes from the fact that here the Dirichlet data that we impose will consist of real-valued affine function. So the first thing that we can say here is that actually here we deal with a nonlinear equation and actually a quasi-linear type of equation. And the fact that this equation is nonlinear comes from the fact that this parameter appearing in our elliptic type of equation depend on the solution of the equation. So here we have the context for this boundary value problem. And in this context, we will state our inverse problem, which will consist of fixing m point at the boundary of our open set omega, m being a number which will be less than n being the dimension of the space, and to consider the inverse problem of determining this quasi-linear term. So this quasi-linear term will be the unknown in the class of inverse problem that we would like to consider from measurement corresponding to the knowledge of the conormal derivative of the solution of this boundary value problem computed at this m different point. So here, the unknown will be the quasi-linear term. The measurement that we consider for determining this quasi-linear term will consist of the conormal derivative of the solution of this boundary value problem computed at this m different point. And our result will be either a uniqueness result and or a stability result, both stated in terms of theoretical result that I will clarify a little later on. But roughly speaking, the idea of the uniqueness is some kind of injectivity, while the idea of stability is to add some kind of continuity to this type of injectivity property. So this is the general statement of our problem. Now, let me give some motivations to this class of problem. And the first thing that I would like to mention is that this class of inverse problem fall into the category of determination of a nonlinear term appearing in an elliptic type of partial differential equation, which is a class of problem which has received a lot of attention this last decade among the mathematical community. Apart from that, this problem that we consider has several physical motivation. The first one being the connection between the voltage and the current density, which will be given by the conductivity that we would like to determine here. So this is the connection that is made between voltage and current. It's given by this class of conductivity. And the idea here will be to consider a general class of conductivity, which will depend on the voltage and on the current that we want to determine by applying voltage at the boundary of the open set and making measurement of the corresponding current flux at this m different point. So here the goal will be to determine this connection between voltage and current density in the context where we do not deal with the classical Ohm's law, but more general class of nonlinear law. So this is the first class of physical motivation that we can give to our problem, but one can also see the appearance of this class of inverse problem in the context of problem of viscous flow, but also plasticity phenomena. Finally, in terms of physical motivation, we can also mention problems of heat conduction when the heat conduction will be actually given by our quasi-linear term, and we want to determine this class of heat conduction term in the context where this heat conduction depends both on the temperature and on the thermal gradient, and this for some class of solution of stationary diffusion equation. So this is the different physical motivation that we can give to our problem. And in the context of its statement, our problem will have also other type of motivation, which will be more related to the mathematical motivation. Namely, our goal here would be to make two important restrictions on the data used so far for solving this class of inverse problem. So here, this idea of restriction of the data will be clarified once we will recall what has been done so far for this class of inverse problem, which will be done a little later on in this talk. But first, let me specify the two important restrictions that we consider here. The first one corresponds to the class of Dirichlet data that we impose at the boundary of our open set, this Dirichlet data, which in practice correspond to the excitation of the system that we apply at the boundary, the measurement being given by the conormal derivative of the solution. So we consider here Dirichlet excitation lying in the set, in an open set of affine functions of Rn, taking values in R, which is a space of dimension n plus 1. So this means that actually we consider excitation lying in a finite dimensional space. And what I would like to emphasize is that if our equation was a linear equation, considering this type of excitation will be equivalent to consider excitation lying a finite number of excitation. So we are at least here close to something that can be related to finite number of excitation, but in the context of nonlinear equation, it will not be finite number of excitation, but excitation lying in a finite dimensional space. So this is the first restriction that we make on the type of data that we use. The second one being that, in contrast to other works related to this problem, we restrict our measurement to at most n point located at the boundary of our open set. So here, our goal in this idea of restricting the data will be to move from this theoretical result that I will present to you a little later on to the numerical reconstruction. And for this, the first step will be actually to reduce the amount of data that is considered often for this type of inverse problem, since usually what is considered for solving this type of inverse problem corresponds to too much data, and it is quite difficult to compute numerically. This is somehow one of the obstructions that has been opposed to the numerical reconstruction considered for this type of inverse problem, which somehow has been missing so far. So we will see that a little later on. So this is the second motivations for our problem. But the second motivation will be clarified, as I said, a little later on, when I will recall what has been done so far for this problem. Okay, so now let me come back to the position of our problem and let me clarify a little more what will be the class of quasi-linear term that we want to consider. And here I will introduce the minimal assumption that we will impose to our quasi-linear term. So first of all, we have this minimal regularity of C3 imposed to this quasi-linear expression. Apart from that, we have this condition. So here, the variable mu will be associated with the solution of the equation, while the variable eta will be associated with the gradient of the solution of our equation. And here, this condition tells us that this quasi-linear term will be of elliptic type, and this ellipticity is proportionate to the dependency with respect to the solution and to the gradient of the solution. In addition to that, this matrix, which will include all this coefficient of our all these parameter appearing in our elliptic equation, will be symmetric. And this allows us, by means of this representation in terms of a matrix valued function, to reformulate our equation as follows in a more simplified way. So this is the first thing that I wanted to say about our equation. Now let me clarify the class of Dirichlet excitation that we will apply at the boundary of our open set. And for the definition of this class of Dirichlet data, we will need first to introduce two parameters, which will be two real parameters, lambda and tau, that will be fixed a priori, along which we add this vector omega, which will be lying on the unit sphere. And here, this real valued affine function, which will correspond to the Dirichlet excitation that we apply at the boundary of our open set, take the following form. Namely, they will be equal to lambda plus tau times the scalar product of x with omega. So this is the class of Dirichlet data that we impose at the boundary of our open set. And this is the class of equation that we consider. And now we can reformulate our inverse problem as follows. So we pick m point located at the boundary of our open set, m being less than n. And what we consider is the determination of this quasi-linear term appearing in our equation from the knowledge of the conormal derivative of the solution of this boundary value problem with the parameter lambda, tau, and omega admitting the following variation, namely for lambda lying along the real line, tau being sufficiently small, and omega lying on the unit sphere. So for this type of variation of this Dirichlet excitation, the different parameter appearing in this Dirichlet excitation that we impose, our measurement will correspond to the conormal derivative of the solution of this type of boundary value problem. So this is the position of our problem. Now, let me recall what is known so far for this class of inverse problem in order to clarify actually the second part of the title of this talk, namely this idea of restricted data. So I will start with some classical formulation of this type of inverse problem. That is the determination of a quasi-linear term from what is called overspecified data. So this statement of the problem is a little different than the one that I have introduced to you, in the sense that we consider first here a quasi-linear term depending only on the solution. So it has no dependency with respect to the gradient of the solution. The equation is considered on omega, which is an open bounded set of R2. So the dimension of the space is n equal to 2. And the corresponding equation is non-homogeneous. And the boundary condition that we impose is the Neumann and not the Dirichlet. So here, actually, if you compare to our problem, we have different type of excitation of the system. The first one being on the right-hand side, which is an internal excitation. The boundary excitation, which will be a Neumann one. And the corresponding measurement will be the knowledge of the solution at the boundary, which is Dirichlet measurement. And from this type of measurement, we want to determine the conductivity of the medium, which will correspond to this quasi-linear term depending only on the solution. So this is the class of inverse problem that is considered in this context of this overspecified data. And this is actually a quite classical formulation that goes back to the end of the 60s with this first result of Cannon of 1967, where this problem was considered first. It has been extended to a theoretical uniqueness result by Piland and Randall in 1988. So this is for the theoretical part. But this inverse problem, in contrast to the one that will be more closely related to what we would like to consider, has received also numerical treatment, namely a reconstruction algorithm based on iterative process considered along with numerical computation, included in the work of Kugler of 2003, but also Egger, Pitchman, and Scott Bloom in 2014. So this is for this first class of problem connected to the one that we want to consider, but a little different in the sense that, for instance, you have here internal excitation, not just boundary excitation. In terms of problem more closely related to the one that we would like to consider, one need to state the inverse problem a little differently. So here, the statement of this inverse problem can be considered as follows. We consider here a quasi-linear elliptic type of equation where the quasi-linear term, which is a matrix-valued function, will be considered as a function depending on the space variable, the solution, and the gradient of the solution. So this gives us this elliptic type of quasi-linear equation stated in quite general context. And the class of inverse problem that we will consider here will be the one where to each Dirichlet data we associate the conormal derivative of the solution of this boundary value problem that we restrict on S, S being an open set of the boundary of our domain. And this gives us information given by what we call the partial Dirichlet to Neumann map, which will be the map that sends each of these Dirichlet data to the corresponding conormal derivative of the solution restricted to this open set S. And from the knowledge of this Dirichlet to Neumann map, the goal is to determine this type of quasi-linear term. This is quite general statement of this problem, and we will see what has been done for this general statement and what can be connected with more precisely with what we would like to consider here. So the first result that we can mention in that direction are results due to Sun in 1996, where Sun treated the determination of a Casilina term, which will be real valued. It takes the following form, and it depends on the space variable and on the solution of the equation. So this result of Sun was extended then by Sun and Ullmann in 1997 into the determination of a matrix-valued Casilina term depending on the space variable and on the solution, in the specific case of dimension n equal to 2, but also in the case where this map will be analytic with respect to the space variable and the solution of the equation. In the more specific case of dimension n equal to 2, we can also mention the work of Harvas and Son, who treated the determination of a matrix-valued Casilina term depending on the space variable and on the gradient of the solution. So this is the first result that has been obtained at the end of the 90s and the beginning of the year 2000. And for all this result has been stated either with dependency combining space dependency and the dependency with respect to the solution, or dependency with respect to the space variable and the gradient of the solution. For the determination of Casilina term combining the dependency that we are interested in, namely the solution and the gradient of the solution, one need to wait the work of Shankar of 2019, extended then by Munoz and Ullmann, where both these authors considered the determination of a real-valued Casilina term depending on the solution and on the gradient of the solution. So this work was then extended into the determination of a real-valued Casilina term combining three classes of dependency, that is space variable, solution, and gradient of the solution, into our two different collaborations. A first work in collaboration with Kartesa, Faiz Mohammadi, Krupschik, and Ullmann, where we have determined this class of Casilina term in its most general statement, namely quite general class of real-valued Casilina term combining these three types of dependency. And the second work with Krupschik and Ullmann, where we have restricted this type of result to some specific type of Casilina term, having dependency with respect to the gradient of the solution only in one direction. And for this specific type of Casilina term, we have been able to treat the determination not with measurement on the full boundary, but on an arbitrary subset S. Namely, we have treated the situation where this set S is arbitrarily chosen, the set where we restrict the conormal measurement of the conormal derivative of the solution of this boundary value problem. So this is the first type of result that we can mention in that direction. And all these results that I have stated are uniqueness result. For stability result, so I recall that the goal of the stability is to add some continuity to the uniqueness. For stability result, there has been actually much less treatment, much restricted treatment. And the result that I have mentioned, one of the results that I have mentioned in that direction, it's maybe the only one that I know actually for Casilina term, is the one that I have obtained in 2023, where I have considered the determination of a Casilina term depending only on the solution of the equation. So apart from this work, I would like also to mention that there is several recent contributions related to this type of problem, namely the determination of a Casilina term, considered in the context of inverse problem for the minimal surface equation. And here, without being exhaustive, we mention the following recent contribution. So this is an overview of what has been done concerning the determination of a Casilina term for elliptic equation. And there's two things that I would like to mention. So first of all the results that I've mentioned here for this problem, which is more related to the one that we would like to consider and not the one with overspecified data, is that first of all, the numerical result or the numerical reconstruction is missing. There is no numerical reconstruction associated with this result, which are mostly theoretical. Secondly, the determination of a general Casilina term, depending on the solution and on the gradient of the solution, is also missing, either from the theoretical point of view or the numerical reconstruction. So this is actually the two different goals that we will have. So we will not treat the numerical reconstruction here, but what we would like actually is to restrict the data in order to at least get close to what would be possible to consider in the direction of numerical reconstruction of this type of parameter. Okay, so now that I have recalled what has been done so far, let me come back to the statement of our result. And let me be a little more clear about the first thing that we need to clarify, that is the forward problem, or more precisely, what kind of condition would guarantee the well-posedness of this boundary value problem 3. So here, we consider the assumption that we have seen before, this ellipticity condition imposed to this matrix valued quasi-linear term, and the symmetry. And we consider our parameter to be the one that will allow us to define our Dirichlet boundary condition. And the first thing that we can say is that for any fixed value lambda, provided that epsilon is sufficiently small, or this parameter tau is sufficiently small, we will have unique existence of a solution of this boundary value problem, which will be sufficiently smooth. So this is the first thing that we can notice. And thanks to that, we can now state our inverse problem as follows. So we will consider the solution of this boundary value problem in this specific context. And we will consider, in terms of measurement for the determination of our quasi-linear term, the knowledge of the conormal derivative of the solution of this boundary value problem with these different parameters that are in this setting, allowing us to refer to the unique solution of this boundary value problem 3. Namely, lambda goes along the real line, tau is sufficiently small, and the smallness is given by this condition, and omega is lying on the unit sphere. So here, and from now on, we will refer to U of index lambda, omega, and tau, the unique solution of this boundary value problem, which is prescribed by this type of Dirichlet data, depending explicitly on this different parameter, lambda, omega, and tau. So this will be the notation that we will use from now on in the next result that I will present to you. So this is the situation for the well-posedness of this boundary value problem. Apart from that, we will need also to impose some condition, some admissibility condition for our quasi-linear term. So this admissibility condition tells you what kind of quasi-linear term you can expect to determine from the measurement that we would like to consider. So the idea is that actually we cannot determine any kind of quasi-linear term. We will have to impose some condition. This condition is actually a technical condition. So the condition that I will introduce to you, roughly speaking, say that we consider quasi-linear term having an orthonormal basis of eigenfunction, which will depend only on the solution. So let me be a little more precise about this condition. So the idea is that the matrix given by A, since A is symmetric, it admits a diagonalization given through an orthogonal matrix capital U. And what we will consider in this diagonalization of this matrix is that the orthogonal matrix depends only on the variable mu associated with the solution, and the dependency with respect to the gradient of the solution of this symmetric matrix will be given only by its eigenvalues. So this is our technical assumption that I present to you in a rough way. And assuming that this condition is imposed, the other condition that we will need in our inverse problem comes from the location of our measurement. So the measurement cannot be considered anywhere. The idea will be that we will fix n point at the boundary of our open set, and we choose this endpoint, which will be the point where we will localize our measurement, in such a way that we can find an orthonormal basis of our n, E1 prime to En prime, in such a way that the outward unit normal vector of our open set omega, computed at this different point x1 to xn, will be sufficiently close to each vector of this orthonormal basis of our n. And this closeness will be explicitly given by this upper bound, which is equal to 1 over the square root of n. So one thing that we may ask ourselves is it possible actually to find this endpoint satisfying this condition? And what happens is that actually this is possible, and this is actually a consequence of what is called the surjectivity of the Gauss map, which tells you that if your open set have sufficient smoothness, the map that sends each point at the boundary of our open set into this outward unit normal vector will be surjective as a map taking values on the unit sphere. So this means that your outward unit normal vector computed at different points of the boundary of your open set will take all possible direction on the unit sphere. So this guarantees you that you will always be able to find such a point. And actually, due to the fact that our open bound is explicit and can be quite high if n is small, or you have small values of n equal to 2 or n equal to 3, you will have important freedom for the choice of this n different point located at the boundary of your open set. So this is the condition that we need for our main result. And now, thanks to this condition, we can start by the statement of our main result, starting by uniqueness result. So as I told you, uniqueness result is given in terms of injectivity, saying that if the data for your two unknown coincide, then the unknown coincide. So for this, we will need to introduce two classes of Casilina term of index j being equal to 1 or 2. We impose to this Casilina term some regularity, which is given in terms of this integer L, which is a priori fixed. We assume that this Casilina term satisfy this condition. They take the following form. This is the condition that we impose. And assume that this endpoint located at the boundary of our open set are chosen in such a way that this condition is fulfilled, this geometrical condition for the location of the part where we restrict our measurement. And after that, we associate to each of these Casilina terms the solution of this boundary value problem, the boundary value problem for A replaced by A of index j, being the solution U of index j. And we state our result as follows. If the solution associated with the Casilina term of index 1 has measurement that coincide with the solution of the Casilina term of index 2, along this variation of the different parameters that we have introduced before and located at this n different point, then what we can prove is that the differentiation with respect to eta being the variable associated with the gradient of the solution, computed to these two different Casilina terms that we consider at lambda at 0 and differentiation at order k, this for lambda on the interval minus r, and this index k going from 0 to L minus 1, so L is related to the regularity of our Casilina term, coincide for the two different Casilina terms. So this is the first main uniqueness result that we obtain in this work. And this uniqueness result is actually not really clear because this is not exactly an identity of the Casilina term. In order to get from this general result an exact identity of the Casilina term, we will need actually to consider a consequence, the first consequence of this result, namely what happens if you have infinite smoothness and what happens if you add an extra analyticity assumption to our Casilina term with respect to this variable eta associated with the gradient of the solution. So in this situation, what happened is that from the same type of measurement, we can fully recover our Casilina term. So this is what we get from this first general theoretical results about unique recovery, which leads to an exact unique recovery, provided that you add this extra analyticity assumption. So this is the first consequence of our result. And what will be also interesting will be to consider the situation actually where we deal not with Casilina term that takes value in matrix of matrix valued Casilina term, but real valued Casilina term. And what happened is that actually in the context of real valued Casilina term, taking the following form, what we can show is that actually we do not need to consider the measurement at n point located at the boundary of our open set, but just one arbitrary chosen point, and we can get exactly the same result, which along with the extra analyticity assumption with respect to the gradient of the solution leads to the full unique recovery of our Casilina term. So here, what is interesting in the second situation comes from the fact that the measurement is considered just at one point and one arbitrary chosen point at the boundary of our open set. Okay, so now let me say a few words about this uniqueness results. And the first thing that I would like to say is that now you're able to compare with what has been done so far for this type of problem and see that actually we make important restriction on the data used so far for this class of inverse problems. The first one being that actually in all the results that I've mentioned to you, the excitation, that is the Dirichlet data that are imposed to the system, are lying in a space of infinite dimension. Here, we met a restriction of this by considering only real valued Affine functions, which are lying in a space of dimension n plus 1. So this is the first important restriction that we make on this class of inverse problem. The other restriction comes from the fact that at least the measurement for this different inverse problem that I have introduced to you before correspond to the knowledge of the conormal derivative restricted to an open set of the boundary, which correspond to an infinite number of points. While here, we restrict our measurement to at most n point, that is 1 point for real valued Casimir terms, and n point for matrix valued one. And this makes our result much more suitable for numerical reconstruction comparing to what has been done so far for this type of inverse problem. In addition to that, actually, we deal here with explicit type of real valued affine function in terms of Dirichlet excitation, which makes it even easier for the numerical reconstruction, since we not only deal with excitation in a finite dimensional space, but some quite explicit and well-known one, that is the real valued affine function. So in addition to this restriction of the data, we give also, as far as we know, the first result of determination of general class of matrix valued Casimir term that combines this dependency with respect to the solution and the gradient of the solution. Okay, so this is the first step for the uniqueness result that we have, but we have also stability result. So the stability, as I said, gives an extra continuity to the injectivity of the uniqueness. And for the statement of the stability, we will need a little more information about the solution of our boundary value problem, and more specifically, its dependency with respect to this parameter tau appearing here. So what we can show is that actually, this dependency with respect to this parameter tau of the solution of this boundary value problem will be CL, provided that your Casimir term has a regularity C2 plus L. And this CL regularity will be considered on a small neighborhood of 0. Thanks to that, what we can consider and what will be the data that we will use for determining our Casimir term will be actually the differentiation with respect to this parameter tau at order k going from 1 to L, of the data that we have used for our uniqueness result, namely the conormal derivative of the solution of this boundary value problem computed at this n different point that we have seen before, and this differentiation with respect to tau is considered for tau equal to 0. So this is the class of data that we will consider. So we will see a little later on why we use this type of data. But anyway, with this type of data, we will state our stability result in the following way. So we consider here Casimir term consisting on product of two terms. First, a real valued term, depending on the solution and on the gradient of the solution, times a matrix valued one, which will depend only on the solution of the equation, that is the variable mu. And after that, we obtain two classes of stability estimate. The first one is a stable determination of this matrix valued part, which is given by this expression. So we have an estimate of the difference of this matrix valued part of our Casimir term with respect to the differentiation with respect to tau of the conormal derivative of the solution of the two different problems for the two different Casimir term computed at these n different points that we consider for tau equal to 0, and for which we take the supremum with respect to the different data appearing at the boundary, at the Dirichlet data that we impose. So this is the first stability estimate that we obtain. And we will see a little later on, but one important point in this stability is that the constants depend only on the open set omega and the n different point where we localize our measurement. For the second stability, our goal will be to determine this extra expression, which gives us actually more information about the dependency with respect to the gradient of the solution. So for this, what we get is actually the stable determination of the differentiation with respect to this variable eta at order capital N of our Casimir term, this real valued part of the Casimir term, computed at lambda and 0. So these terms are actually symmetric tensor of rank capital N, and we consider them with respect to a norm of tensor of rank capital N. And the estimate of this term are considered as a supremum with respect to lambda lying on minus r being a parameter that we fix a priori. So we have here some extra stability estimate without giving too much detail about it. It corresponds no longer to a Lipschitz stability one, but to a Holder one. And in contrast to the previous case, the constant have several extra dependency. And this stability estimate, in contrast to this one, will require this a priori estimate of the unknown that we would like to determine, coming from this function psi. So this psi gives us the a priori estimate that we impose to our class of Casimir term. So this is the different dependency that appears in this constant in our second stability estimate for the extra term appearing in our Casimir term. So this is the first stability result that we obtained for this problem. And again, as in the previous case, we can get some improvement of this result by considering not matrix valued Casimir term, but real valued Casimir term. And in this situation, we can again replace everywhere the measurement at this n different point by the measurement at one arbitrary chosen point located at the boundary of our open set and get exactly the same type of result as we have seen before. So this is the situation for our stability result. Now let me say a few words about the stability result. And let me first mention the first class of stability estimate, namely this one. So what is interesting in this stability estimate is actually that we do not impose any condition on this matrix valued function in our result. So this condition actually is not used here since the constant does not depend on psi. And what happened is that this stability estimate does not require any information about the quasi-linear term that we would like to consider since the constant is completely independent of the quasi-linear term that we consider here, this quasi-linear term A. So it has no dependency with respect to that, no requirement of a priori estimate, and this stability estimate confirms what I have already observed in my work of 2023, namely that for this part, the part of the quasi-linear term that depend only on the solution, we obtain an unconditional stability estimate or some kind of robustness of this stability estimate with first a Lipschitz stability estimate, but also a stability estimate that will be completely independent of the unknown that you would like to determine. This is actually something that you do not often see in inverse problem, and moreover for nonlinear inverse problem, like the one of the determination of a quasi-linear term. But this is something quite interesting that happens here and make this result quite interesting in terms of stability result. So, of course, when we want to determine more information about the dependency with respect to the gradient of the solution, our stability estimate, which was Lipschitz, degenerate into a holder one. And in contrast to the previous case, we need this time a priori estimate. The a priori estimate of our unknown are given by this condition, namely that this quasi-linear term of index j are open-bounded by some expression that does not involve the index j. This is the restriction that we make for the resolution of this nonlinear problem, which is our inverse problem. However, in both cases, for these two stability estimates, what we get is actually much better than most of the stability estimate considered for elliptic equation, which are of logarithmic type. And the idea of improving this type of stability estimate can be, again, an interesting tool in the context of numerical reconstruction, where, as observed by Cheng and Yamamoto, the quality of the stability estimate can improve the numerical reconstruction and the rate of convergence of numerical reconstruction by approach such as Tikhonov regularization. It allows, for instance, to have a good choice of the regularization parameter. So this is the thing that we gain, the gain that we will have in terms of potential numerical reconstruction, that is the next step, from this type of stability estimate. Okay, so this is what I wanted to say about this result. Now, let me give you an idea of the proof. And I will mostly focus actually on the main things that we analyze in this work, namely the asymptotic properties of the conormal derivative of the solution of this boundary value problem as tau goes to 0, computed at this n different point, and for this type of Dirichlet data with the parameter lambda admitting variation along the real line and the variable omega on the unit sphere. So this will be actually the key ingredient in our analysis, and I will describe this part. Instead of getting too much into the detail of the proof, I will just focus on this part. So let us see what will be the asymptotic properties of this data, that is the conormal derivative of the solution of this boundary value problem as tau goes to 0. So the first thing that we would like to see is actually what happened when tau is exactly equal to 0. So the value of tau equal to 0, what it will give us for our data, that is the conormal derivative of the solution of our boundary value problem computed at this n different point. So to see that, let us first consider the conormal derivative in its initial definition. And let us see what happened when we send tau to 0. To see what happened when we send tau to 0, one needs to consider the solution of the boundary value problem 5 when tau is equal to 0. And if you consider this as the term u of index 0, you will get that the conormal derivative of the solution of our boundary value problem as tau is fixed at 0 will be given by the following expression. And now what we need actually in order to understand what happened here is actually what is this guy? To understand what is this guy, let us first focus on what happened at the boundary of our open set. At the boundary of our open set, if tau is equal to 0, this map u of index 0 will be equal to the constant lambda. But what happened is that actually, if you take a look at the equation, constant function or solution of this equation. So if your boundary condition is the constant, thanks to the uniqueness, what you can say is that actually this map, which will be equal to lambda at the boundary, will be equal to lambda everywhere. Because lambda is also solution of the equation, and we have uniqueness of the solution. So this tells you also that the gradient of u of index 0 will be uniformly equal to 0. And if you take a look at this conormal derivative of the solution fixed at tau is equal to 0, you see that you have here the gradient. And since you have here the gradient, what you can say is that the conormal derivative of the solution of this boundary value problem computed at this different point for tau is equal to 0 is equal to 0. So what you can see is that actually the asymptotic properties as tau goes to 0 of order 0 will not give you any information. So you need to push a little further these asymptotic properties and to consider the asymptotic properties at order 1. To do that, what we can apply is actually Taylor formula. And thanks to Taylor formula, what we know is that if we push the asymptotic properties as tau goes to 0 of this data, we will have this expression with this coefficient in the asymptotic properties as tau goes to 0, which will be given by the differentiation with respect to tau of this map as tau is equal to 0. So in order to have an explicit formula for this asymptotic at order 1, we need to have an explicit expression of this Taylor coefficient. So to do that, we need to consider the differentiation with respect to tau of our data. And the idea here is actually to recall that our data is given by this map, which is the product of two maps depending on the parameter tau. And if you apply the differentiation with respect to tau to the product of these two maps, you will have two different expressions. The first one with which you apply the differentiation with respect to tau to your Casimir term. The second one where you apply the differentiation with respect to tau to this map gradient of u. So here, this u of index 1 will be actually the differentiation with respect to tau applied to your solution fixed at tau equal to 0. Using again what you have seen before, namely that this expression u of index 0, which will correspond to the value of your solution for tau fixed at 0, is the constant map, we will see that in this expression of the differentiation with respect to tau of the conormal derivative of the solution of our boundary value problem, this part will be equal to 0, and the remaining part will be only this one, where here again u of index 0 will be replaced by lambda, and the gradient of u of index 0, which is the gradient of a constant map, will be replaced by 0. So we have something that is almost explicit in this Taylor coefficient. The only thing that is missing is this function u of index 1, which is a differentiation with respect to tau applied to the solution of this boundary value problem as tau is equal to 0. So we need actually to clarify what is this map. And to clarify what is this map, we will need to see what happens if we apply the differentiation with respect to tau, both to the equation and to the boundary value condition, the Dirichlet boundary value condition. So if we do so and we restrict the value as tau is equal to 0, what we get is actually that this function u of index 1 will be solution of this boundary value problem with an elliptic type of equation with constant coefficient and a Dirichlet boundary condition which is given by this linear function. But what happened here actually, and what gives us some interesting information about this function of index u1, is that actually linear function or solution of this elliptic equation. So again, using the uniqueness of the solution of this boundary value problem, what we can say is that this function u of index 1 is actually this linear function that we impose at the boundary. This means that its gradient is actually a constant vector, that is the constant vector omega that we have imposed at the boundary. And now, using this, we can have something completely explicit for this asymptotics at order 1. Namely here, we will have this type of asymptotics with this Taylor coefficient corresponding to this matrix valued function A that we take at lambda and 0, to which we apply the vector omega, and we take the scalar product of this with respect to the outward unit normal vector, computed at this n different point where we consider our measurement. So this gives us this asymptotics of our data as tau goes to 0 at order 1. And the idea, either it is from the uniqueness point of view or the stability, is to compare these two asymptotics and to say that, so since we have access to this type of data, we have also access to this asymptotics, and therefore the two coefficients in this asymptotics for the two different Casimir terms coincide, which tells you, first of all, that we manage here to determine this type of coefficient, this expression, for this n different point. And using now the geometrical assumption that we have imposed to our outward unit normal vector, we manage to recover from this map the coordinate of this vector, A of lambda and 0, applied to this vector omega, on this orthonormal basis, E1 prime to En prime. And using the fact that we have the coordinate of this vector, we can recover fully this vector. And finally, using the fact that we have access to this vector for all omega on the unit sphere, we can recover the full matrix A. This is actually how we get the information about our Casimir term, the first step of our process. The next step will be actually to extend the asymptotic properties of our data to order 2. So the asymptotic properties at order 2, again, by means of Taylor formula, take the following form, and it involves a differentiation with respect to tau at order 2 applied to our data. And again, what we need actually is something explicit for this data. So here, the idea will be, again, to apply a Leibniz formula for the differentiation of product of function, and to consider the differentiation with respect to tau at order 2. And what we get, without getting into the detail, is a first expression involving the differentiation with respect to eta applied to our Casimir term that we consider at omega, and we apply to omega and take its scalar product with this outward unit normal vector computed at this n different point. So this is the extra term that appears in our coefficient, plus a map H that will depend on what we have recovered at the asymptotic at order 1, namely these coefficients. And finally, a last one, which will not be explicit. So this is the only one that will not be explicit or will have extra dependency with respect to the new parameter. That is the one involving the gradient of u of index 2, where u of index 2 will be given by the differentiation with respect to tau at order 2 applied to the solution of this boundary value problem as tau is fixed at 0. So in order to have everything that is clarified, again, we need to give an explicit dependency of this map, so not have explicit formula, but at least give its explicit dependency of this map u of index 2. And what we can do is, again, apply the differentiation to our equation and to the Dirichlet boundary condition to see that actually this function u of index 2 will be solution, again, of this elliptic equation with constant coefficient. But the equation will be non-homogeneous. It will be given by the divergence of this vector valued function, capital K being given by the following map. In addition to that, the Dirichlet boundary condition of U2 will be equal to 0. This is expected since here, actually, we apply differentiation with respect to tau at order 2 to a map with dependency in tau is linear. So this is what we get here. And the point here will be actually that the dependency that we'll have for U2 will be given by the dependency that we'll have for this divergence of this map capital K. And what happened is that this map capital K takes the form of the differentiation with respect to eta of our Casimir term plus a map K prime. And here what happened is that this map K prime depends only on the terms that we have determined at the first step, that is the one that we already know, And since this vector is constant, the divergence of this map capital K will be equal exactly to the divergence of K prime, which means that actually here on the right-hand side of our equation, we have something that depends only on what we have recovered at the first order asymptotics, and the same will be true for U of index 2. So this tells you that the asymptotic at order 2 will be given here explicitly by this new expression, depending on the differentiation with respect to eta of our Casimir term, plus some map E that depend only on what we have recovered at the first order asymptotics. And now again, comparing the two different asymptotics, using the assumption that we impose on our quasi-linear term and the geometrical condition, we can recover the differentiation with respect to eta of our quasi-linear term computed at lambda and 0 on omega, and again using the fact that omega can be arbitrarily chosen on the unit sphere, we recover the differentiation with respect to eta of our quasi-linear term computed at lambda and 0. So now the idea for the next step will be to go along an iteration process. And so roughly speaking, the idea would be that first we determine the following information. That is the differentiation with respect to eta at order capital N of our quasi-linear term, computed capital N time at the same vector omega, and to use the condition that we have imposed into our quasi-linear term, namely that the dependency with respect to eta appears only at the eigenvalues of this matrix. So here we need only mostly to recover the eigenvalues of the matrix, which will be real valued function. And in this context, the differentiation with respect to eta at order capital N of real valued function will be given by symmetric tensor of rank capital N. And the final step will be to combine this with a polarization argument in order to, at the end, recover the differentiation with respect to eta at order capital N of our quasi-linear term computed at lambda and 0, and to complete our proof. So this is, roughly speaking, the idea of the proof. And what I would like to mention here is actually something that need to be emphasized, is that one important technical argument that we use here is actually this linearization techniques, which consist in applying differentiation with respect to this parameter tau, what we have considered all along, this parameter tau that we have imposed here. This differentiation with respect to this parameter tau correspond to what is known to be the linearization techniques. This linearization techniques goes back to the work of Isakov of 1993. It is actually one of the most important tools used so far for recovering nonlinear term. So in its work of 1993, Isakov considered the linearization at order 1. This work has been extended to linearization at order 2 by Sun and Ullmann, and finally considered by Kurilev, Lassas, and Ullmann in terms of infinite order linearization. So this is one of the most important tools for solving inverse problem of determining a nonlinear term, and it has been used by many authors. Here, I mentioned several of them without being exhaustive. But what I would like to emphasize here is that in contrast to most of this work, what we use here is not an idea of transforming this type of inverse problem into some density of product of solution of linear elliptic equation, but instead we consider explicit asymptotic properties of our data, and we extract the information about the unknown from this explicit type of asymptotic properties. So this makes a difference between our approach and the one that has been considered for this type of inverse problem. And this is also somewhat connected to the type of quasi-linear term that we consider that are independent of the space variable. But even for this type of quasi-linear term, our approach is new. And this is also the main reason why we get rid of this important class of data that has been used for recovering this type of nonlinear term. And we managed to get the restriction of the data that I have introduced you before. Okay, so let me now complete this talk by some prospect. But before giving some prospect, I would like to say a few words about related problems. Namely, some problem that I state in a simplified way, so the result that we obtain is more general one. Namely, a result related to the determination of a semilinear term appearing in an elliptic equation. So here, in contrast to what I have introduced you so far, we deal with a semilinear elliptic equation to which we impose some more general Dirichlet boundary condition than the one that we have seen before. And our goal is actually to consider one point located at the boundary of our open set and to determine the semilinear term appearing in this elliptic equation from the knowledge of the normal derivative of the solution of this boundary value problem computed at this single point located at the boundary of our open set. So here we can consider different situation for the Dirichlet excitation. It can be either lying on a space of dimension 1, so it admits a variation along a line, or it is fixed. The case where it is fixed gives you result with single measurement since you have just one excitation and one corresponding measurement. And here, what I would like to say is that actually in the recent work with Liu, Wang, and Zheng, we have treated the theoretical stable determination of this type of semilinear term from this class of data. And this theoretical stability result have been considered along with a reconstruction algorithm and corresponding numerical computation associated with our reconstruction algorithm, which was based on Tikhonov regularization approach. The idea was actually to treat the determination of this semilinear term as a source term, and then to include the dependency with respect to the solution in order to determine not just the source term, which is the following term, but exactly the semilinear term that we want to consider. So this is actually some specific type of approach that we have considered to treat both theoretical results for this problem, but also treat the numerical reconstruction. And here, actually, this related problem allows me to introduce the different prospects that can be associated with this problem, namely moving from the theoretical result to the numerical reconstruction. So the first thing that we can do in that direction would be actually to first try to make some restriction on the type of quasi-linear term that we want to determine. So first try to determine quasi-linear term that depend only on the solution, so get rid of this dependency with respect to the gradient of the solution, and to try an approach which can be compared to the one that we have considered for dealing with the numerical reconstruction of this type of semilinear term. The second one will be actually more general. It will consist in the idea of adapting this theoretical result that we have considered into the direction of numerical reconstruction and see how we can derive a numerical reconstruction algorithm based on this type of theoretical result, and how this theoretical result can be used for dealing with the next step, that is the numerical reconstruction. Finally, the last step, which will be actually both to be considered in the theoretical direction and the numerical reconstruction, will be to extend this result considered for scalar elliptic equation into system of elliptic equation, including, for instance, Labé systems. Okay, so that's all I wanted to say. Thank you for your attention.